So today we are going to discuss about DAC 4-bit digital to analog and to analog equivalent values. Okay, so let us see the applications, go through this slide, and before that we have to see why DAC is required. It is also explained in this slide, go through it, and it also includes the applications. Let us start the DAC circuit diagram. So this is the circuit diagram of DAC and 4 data input, and it is theoretical equivalent value also tabulated. Let us see practically how to implement this. So assemble the circuit according to this video and follow according to that. You see that the output is 100% sure. So here that green color resistors what I have shown is all 2K resistors. Out of that I have selected 4 resistors as a 4-bit data, that is binary data, and 3 1K resistors and 6 2K resistors is here. Out of it 4 resistors is collected and one operational amplifier, and it is connected. Say initially what you have to do is connect all 4 bits to high. That means all 4 bits are 1 1 1. According to theoretical value it is 3.1. See, observe that I got 3.2. That shows that our circuit is working. Now you have to follow the tabular column starting from 002 01 10 11 in the order of 111. See that when I connect to 10 I got 0.29 something, and you keep on do in the same order and see that the consecutive difference between the two readings should be 0.2. Okay, that is the step difference. So plot this on the graph sheet and monitor the output. It appears as a staircase. Okay, see, when R is connected it is 3.1 according to that. Let us say the part 2 staircase generator on CRO. So every time you have to understand the applications of that, and before that you have to see how to settings you have to do in function generator, because we are going to generate staircase at the frequency of 1 kilohertz. Adjust the frequency 1 kilohertz and select the range, and you have to select the function key for the pulse or square waveforms here, and adjust the amplitude for 5 volt peak to peak. This is the initial stage you have to set. After that connect plus or minus 12 volts for the op-amp's power supply and 5 volts for the data input. Here 5 volts we are going to give through 7493 IC, and it is mod 16 counter, and all data 4 data outputs are you are going to connect to the inputs of the outputs of the 7493, which generates square waveforms in the order of mod 16 counter. So as soon as you switch on the power supply, which is 5 volt for 7493 IC, see according to this. Okay, suppose if you are not getting the output, what you have to do is take the CRO positive terminal and check, and each one from MSB to LSB you have to get the square waveforms, and each square waveform and divided by 2 divided by 2 divided by 2 like that. So you will get mod 16 counter output, and it is each output is connected to a 4 bits, and finally the op-amp's output will be square waveform as shown in the CR. You can count here the steps is 16. So here you have to measure the step size, full scale step size, and each step size by multiplying with the volts per scale, and you can calculate the resolution of the waveform. Monitor here, see that the whole assemble of the segment of the power supply, CRO and all those things like this. I think it will help you. Try. All the best.